Okay, so I hope that video was helpful for you to visualize the behavior of retaining walls. Now in this video we're going to dive a little bit deeper into retaining walls and answer some questions from the ARE. So that video demonstrated how the retaining wall on the left here was actually more efficient when resisting overturning and sliding. So from a structural engineer's perspective, we would prefer to design retaining walls like the one on the left. However, as I mentioned in the previous video, from a constructability standpoint, the retaining wall on the right is preferred because we would be cutting back less soil. So ultimately, the location of the wall along the footing matters. And just as with pretty much every element in a building, there is some give and take, pros and cons to where you place that wall. And the discussion needs to take place regarding whether we want to prioritize efficiency or constructability. Now, I've used the words overturning and sliding a few times in this video already, and they were mentioned in the previous video as well. Now we are going to look at all three stability modes of failure for our retaining wall. First, as the previous video mentioned, we have the lateral pressure of the wall that is causing an overturning moment about the point Q. That lateral pressure is resisted by the soil pressure, the vertical soil pressure, on the backspan or the heel of the footing. If the overturning moment exceeds the stabilizing moment, then we have an overturning failure. And as the video mentioned, the main method for resisting overturning in a footing is to extend this footing back further and gain more vertical soil pressure. The next mode of failure is when we have a horizontal soil pressure that exceeds the frictional force underneath the footing. And this causes a mode of failure called sliding. And there are a couple of methods for mitigating sliding in a footing that I will mention in just a moment. Finally, we have a third mode of failure that looks a lot like the first, but it is quite different. So as you can imagine, just as with any footing, there is weight to this structure that needs to be resisted by the bearing pressure, the soil pressure underneath. The soil pressure also tends to increase towards the toe of the footing, this side of the footing, to resist the overturning moment that's generated by this horizontal pressure on the back. If that maximum pressure that's applied at the toe of the footing exceeds the allowable bearing pressure of the soil, you could have settlement occur, and that footing could start to sink. So this would be a bearing pressure failure. So with the first mode of failure, we have adequate bearing pressure underneath, and so the footing does not dip down at all. However, it overturns due to an insufficient stabilizing moment about the point Q. With the bearing pressure failure, the entire footing actually sinks below where it initially started. So those are our three primary stability modes of failure for a retaining wall. Now it's important to note that retaining walls can also fail due to overstressing of the rebar or the concrete. So in this example, if we have insufficient reinforcing on this face of the retaining wall, then we will end up having cracks in the concrete, which of course is a huge problem because we could end up having water in those cracks, which could rust this rebar and eventually lead to a full failure. Now this type of failure would be considered more of an internal overstressing failure, and not a global stability failure like those listed above. So with all of that in mind, let's move on to some ARE example questions. So this question asks, what is the total lateral force exerted by the Earth against the retaining wall shown, per lineal foot of wall? Assume the pressure of the retained earth to be equivalent to a fluid weighing 30 pounds per cubic foot. So 30 pounds per cubic foot, that is our equivalent fluid pressure. And what they mean by per lineal foot of wall is you can imagine that this section that they've cut is a section looking through a long piece of wall, and for the purposes of analysis, we choose to look at 1 unit strip of the wall. So in global terms, all of these answers are actually in pounds per linear foot of wall. And that's important to keep in mind as we start solving this problem and looking at our units. So let's start with a diagram on the right. So this is the equivalent fluid pressure that is applied to our wall, and it has a depth of 10 feet. So if the lateral fluid pressure is equal to 30 pounds per cubic foot, that means that as we move down along this wall, the pressure increases per foot until we reach the bottom, this 10 foot, where we have 30 pounds per cubic foot times 10 feet. And so that maximum pressure at the bottom is equal to 300 pounds per square foot. Now, the question is asking what is the total lateral force exerted by the Earth against the retaining wall. We currently have a pressure in pounds per square foot, and we want a force given in pounds per foot. So what we're looking for is the equivalent point load, we'll call it, that is acting against this wall. So what does this force F equal? Well, as we've done with these distributed loads before, this is a triangular distributed load, so we will have that the force is equal to 300 pounds per square foot times 10 feet, and since it's a triangular distributed load, times 1/2. And we get 1,500 pounds per unit strip foot. And that is our final answer, which is answer C. Now, we can also take this question a few steps further by calculating the overturning moment and the resisting moment. So this question doesn't actually provide enough information for us to know what the resisting moment would be, but we can solve for the overturning moment, and then I'm going to provide the remaining information that we need in order to solve for the resisting moment. So starting with the overturning moment, we know that our force is equal to 1,500 pounds per lineal foot. And in order to calculate the overturning moment about this point Q, we need to know its perpendicular distance. That distance we can of course obtain through geometry. Since it's a triangular distributed load, we know that the force acts through the center of this shape, which happens to be 1/3 from the base. So 1/3 times the height will give us that distance. Or we could take 2/3 times the height in this direction. So if we take that force F and multiply it by 1/3 times the height, we get the overturning moment. So if I plug in those variables, I get 1,500 pounds per foot times 1/3 times 10 feet. And we get a value of 5,000. Moment is of course given in units of force times a distance, and so this would be pound-feet, and since we're looking at a unit strip method, it would be pound-foot per foot for our overturning moment. Next we can solve for the resisting moment that's provided by the soil on the back of the footing, or the heel of the footing. And for that, we first need to know the density of the soil. So the density of the soil is not going to be the same value as this equivalent fluid pressure, this 30 pounds per cubic foot. In fact, it's typically going to be much higher. In fact, the density of about 120 pounds per cubic foot is fairly typical for soils. You can recall that the density of concrete, if it's normal weight concrete, reinforced, it's typically 150 pounds per cubic foot. So now that we have this value, we can calculate our resisting moment. So we need to first find this equivalent point load on the backspan of the footing that is equal to the weight of the soil. So that weight of soil is going to be equal to the density of the soil times the depth. Here we have 9 feet of depth of soil, given that the depth of the footing is 1 foot, and so that would be the weight of the soil in terms of pounds per foot along the length of this footing. And as before, when we solve for equivalent point loads given a uniformly distributed load like this, we need to multiply by the width. And so overall, the weight of soil on the back of that footing is going to be 120 times 9 times 8, which equals 8,640 pounds per linear foot along the length of the footing going in and out of the page. Now to calculate the resisting moment, we take that weight, at 8,640 pounds per foot, and we multiply by the perpendicular distance to Q. I'm going to add one more dimension here, 2 feet. So that perpendicular distance is 8 feet divided by 2 plus 2 feet. And we get a resisting moment equal to 51,840 pound-feet per foot. And as you can see, this footing has no issues with overturning, as the resisting moment is much, much greater than the overturning moment. And if we wanted to, we could calculate the factor of safety, which is equal to the resisting moment divided by that overturning moment. In our case, it would be 51,840 divided by 5,000. So the factor of safety would be equal to 10.3, which is a very large factor of safety. And so this footing could easily be trimmed back, provided, of course, that we have no issues with either soil-bearing pressure or sliding. It's possible that we would have to keep this footing this large, even though we have such a high factor of safety for overturning, if we either had very low soil bearing capacity or a very low coefficient of friction. Now, moving on to the next example question. This question asks, all of the following may increase the sliding resistance of a retaining wall, except, and we have 4 possible choices. So if you can recall, a sliding failure occurs when our lateral pressure of soil exceeds the friction that's provided beneath the footing surface. So let's look at our options. Option A provides an additional integral key to the footing, which I've shown below here. Of course, this key would provide a lateral pressure going in the opposite direction of the pressure that's applied. And so yes, this would be a good option for providing additional sliding resistance. Next we have making the footing wider, or increasing its length in this direction. And here we are providing more surface area underneath, and therefore a larger frictional force to resist our lateral soil force. And so again, yes, this would be a good option for increasing the sliding resistance. Next we have increasing the depth of the footing. And while this doesn't increase the amount of surface area underneath the footing for friction, what it does is it provides more weight on top. And as you may recall from your physics courses, a heavier object is going to provide more frictional force than a lighter object with the same coefficient of friction. And so this is also a possible option for increasing the sliding resistance of the retaining wall. The only option that is remaining is increasing the amount of reinforcing steel in the footing. And as I mentioned above, reinforcing doesn't have anything to do with the global stability failures of a retaining wall. And so this would not be a good option for increasing the sliding resistance of the wall, and therefore D is our answer. Now, speaking of reinforcing, our final question asks, for the retaining wall shown below, which faces are in tension, noted as T, and which are in compression, noted as C? When considering questions like this regarding the behavior of a structure, the first thing you should try to consider is what does the deflected shape look like? As you can recall from the foam demonstration, when you bend that piece of foam, it becomes very clear which side is in compression and which side is in tension by looking at the stretching of the fibers. That same thought process can be applied here. If we think about how this soil is pushing against this retaining wall, and we draw its deflected shape, this stem here can be considered as a cantilevered wall. So this joint here at the base, since it's integral with the footing, is a fixed condition, and up here there's nothing bracing the top portion of this wall, so it is a cantilever condition. And so its deflected shape will start perpendicular to the footing, and then it will lean to the right as it's being pushed by the soil. And so when we look at this deflected shape, we can see that there is tension along the back face. So from that, we can eliminate answer C. Next, if we consider the forces that are applied to the footing underneath, namely the soil-bearing pressure underneath the footing and the weight of the soil on top, we can see that the force pushing up from underneath is greater at the toe, and the soil pressure pushing down is much smaller, and so the toe will want to bend in this direction. And therefore, there is tension on the bottom face. So from that, we can eliminate answer A. Lastly, for the heel of the footing, you can see we have less pressure pushing up from the bottom and more pressure pushing down from the top. And so the heel of the footing has a tendency to deflect like that. And therefore, there is tension along the top face. And therefore, we eliminate answer B and choose D. Now, given what we've just learned from this question, we can also answer where we would want to place reinforcing in our retaining wall detail. Of course, reinforcing will go along the tension face of the wall. And so, for a cantilever retaining wall like this, we would have reinforcing designed along the back face, touching the soil here. That would turn and go along the bottom face of the toe of the footing. And then we would also have reinforcing along the top face of the heel that extends through like that. And so that would be our primary reinforcing. Depending on the thickness of this wall, we would likely also place some simple minimum reinforcing or shrinkage and temperature steel along these faces as well. But the primary reinforcing would be what's shown in purple. So I hope you found that helpful. That's all that I have for you regarding retaining walls. So with that, good morning, good afternoon, and good night, and I'll see you next time.